Ladies and gentlemen, today we dive into one of the most dramatic and critical transients in pressurized water reactor safety analysis, the main steam line break, or MSLB. The moment a main steam line ruptures, everything changes instantly. In steam generator 1, secondary side pressure plummets, sometimes below atmospheric levels. That collapse causes a sharp drop in saturation temperature. The result? Saturated steam flashes into superheated vapor, boiling explodes in intensity. Heat transfer from the core surges. Initially, this is good. The core is cooled rapidly. But beware, too much boiling can lead to dry out and film boiling, where heat transfer becomes inefficient and unpredictable. The primary coolant temperature begins to nosedive. That's right, overcooling. While it enhances heat removal, it also introduces thermal stresses, uneven cooling, and crucially, reactivity fluctuations. Within seconds, the reactor protection system responds. Scram. Control rods slam in. Fission power crashes down to decay heat levels. But the overcooling continues. The cold primary loop near SG1 begins to shift the balance. The core may be subcritical, but the stage is now set for reactivity feedback, an invisible tug-of-war. This is where reactor physics takes center stage. Moderator density begins to shift. As coolant density drops, perhaps from local boiling, moderation weakens. Negative reactivity enters, reducing power. But if emergency cooling injects cold water, moderator density spikes, and with it, positive reactivity. Enter the Doppler effect. As fuel heats, U-238 absorbs more neutrons. Fast, automatic, and negative reactivity is inserted. It's the reactor's own heartbeat stabilizing itself in milliseconds. These feedbacks, moderator and Doppler, are the safety net. The core balances on a knife edge, but it does not fall. At around 70 seconds, SG1 is isolated. The leak is cut off, but now, heat removal drops. Decay heat keeps coming. Coolant temperatures rise again. Yet, reactivity remains controlled. Negative feedbacks dominate. Power decreases. The system leans toward equilibrium. And safety is gradually restored. This accident challenges every safety barrier: overcooling, positive reactivity insertion, asymmetrical core behavior. But our defense in depth holds. Scrams work. Feedbacks regulate. Valves isolate. Systems respond. Even under conservative assumptions, a stuck rod, maximum reactivity, worst-case delays, the reactor stays safe. That is the hallmark of robust nuclear safety. The MSLB accident is not just a scenario. It is a test of engineering foresight, physics, and human preparedness. Through layered defense, intrinsic feedback, and rigorous design, we ensure that even in the face of violent transients, the core remains intact, and the public remains safe. Thank you.